Hello, everybody. My name is Rafael, and today I will be. It's my honor to introduce to you guys Alejandro Saucedo, and he's going to be presenting production machine learning monitoring, outliers, drift, explainers, and statistical performance. So Alejandro is the director of machine learning engineering at Seldon Technologies. He leads large-scale projects implementing open source and enterprise infrastructure for machine learning orchestration and explainability. Alejandro is also the chief scientist at the Institute for Ethical AI and Machine Learning, where he leads the development of industry standards in machine learning explainability, adversarial robustness, and differential privacy. With over 10 years of software development experience, Alejandro has held technical leadership positions across hypergrowth scale-ups and has a strong track record building cross-functional teams of software engineers. Without further ado, Alejandro, I give you the floor.
Awesome. Yeah, thank you so much. I think there's quite a lot of people in the chat. I'd be very keen to keep this interactive. So as we go, if you have any questions, please feel free to drop them. There's quite a lot of content, so let's dive straight into it. So I think the introduction was pretty well covered. Just to give a bit more about my day-to-day. So as mentioned, I work at Seldon as engineering director, where we build and develop one of the most popular machine learning deployment, monitoring, and explainability platforms in Kubernetes, which is currently used across dozens, if not hundreds, of organizations. And I also lead a research center that focuses on the development of frameworks and tools for the responsible operation and development of machine learning systems. But today what we're going to be doing is we're going to be diving into machine learning monitoring. And this is basically in the context of production models. We're going to be talking about some of the key principles for efficient monitoring, some patterns that you can adopt as practitioners, and some hands-on examples showcasing the techniques. One thing to emphasize is that this is going to be a high-level talk, but also a very practical one. You will be able to find all the material in this link. So if you want to try it out yourself, please do give it a shot. All the code and all of the tools are provided there. And because it is largely open source, you can actually try it yourself. So yeah, please do feel free. And if there are any suggestions, do feel free to share them as well. So just to get started, to set the scene, we all know that production machine learning systems are hard. The reason why this is the case is because there is a large amount of specialized hardware that is involved, things like GPUs or TPUs, or perhaps even large amounts of memory. There are complex dependency graphs, there is a large amount of compliance requirements, and there is a need for reproducible environments of the different components that are involved. And then on top of that, you are dealing with the concept of scale. So this is no longer just a single model or a dozen set of models that are produced by yourself as a data scientist, but perhaps it may be several teams or even several business units that are actually creating these different models. And I just saw that in the question in the chat, somebody's asking for the link. I just shared it again, so you can find all of the resources there. So we can all agree that contrary to popular belief, at least before, as no longer that is the case, we are in the MLOps World Conference, so I'm preaching to the choir here. But we all know that the model, the life cycle of the machine learning model actually doesn't end once it reaches the desirable accuracy or desirable performance. If anything, it only begins when we put it into production and it starts being consumed by other applications and by other use cases. So from that perspective, we now need to understand, well, we've spent a lot of time trying to identify what are the best practices in regards to the infrastructure and the experimentation and training of the model, the data governance, the systems, the training systems. But now what about the production components? So we're going to actually delve into what that looks like. We're going to be covering a use case, deploying a model as a microservice into a scalable infrastructure. We're going to be assessing what are the different types of monitoring that we can introduce, including microservice monitoring, statistical performance, outlier detection, drift detection, and explainability, all of which you'll be able to try yourself and you'll be able to adopt if you already have some models in production. So we're going to take one of the hello worlds of machine learning. So this is a CIFAR 10 classification example. This is a model which basically takes an image as an input, and the output is a classification of one of 10 different classes. So in this case, the input is the image of a truck, and the actual prediction would be this vector that says, I believe the class is number 10, or in this case, index number 9. So that's basically the model that we're going to be taking. This focuses on the production machine learning models. So we're not going to be delving into the nuances of the training, although if you want, you can train this ResNet 32 TensorFlow model from scratch. It's going to take a couple of hours probably, but we're going to be able to leverage some of the utilities from one of our open source libraries that is going to allow us to get this pre-trained model. Now what we can see here is that in Python, if we actually run model.predict, with the input being this image, the output is going to be which class is that image. This is the model that we're going to be productionizing, and what we're going to be using to productionize this model is this open source framework called Seldon Core. This is another open source framework that we've developed. It is one of the most popular, if not the most popular, machine learning deployment and monitoring framework in Kubernetes. And we currently actually just hit our 1 million number of models deployed, at least from the metrics. There are actually many more, but are not reported. With, I think it's about, something like 100,000, is it like nodes? Something crazy. But yeah, it's basically very popular. And what it allows you to do is to convert either your model binary, what we just had, our TensorFlow binary, that would be an actual artifact, or your code, to convert it, your code that actually would perform the custom logic to predict, and convert it into a fully fledged microservice that you can deploy in a Kubernetes cluster that would have a RESTful gRPC and Kafka interface that you can then just interact. So you go from model to microservice with these abstractions that simplify the interaction. What it actually looks like in practice, you either start with the artifact or with your code, and you use the source to image utilities that we provide to convert this code into a Docker image, or you're able to deploy your artifact directly into one of the prepackaged servers like TensorFlow Serving, like Triton. All of the popular servers are actually supported. And what you get with is with the ability to simply select all of the attributes. In this case, we're saying, I want to deploy this artifact, which is basically this ResNet 32 TensorFlow model, and I want to use the TensorFlow server. Once you actually put this into your Kubernetes cluster, all of the components, pods, services, the networking configurations gets created for you. And then you can actually just send requests to your deployed model. In this case, we're using the Python request library. We are sending a image, and we are seeing as a response the prediction of the classes. Why am I rushing through this? Because this talk doesn't focus on the productionization of models. There's probably other 10 talks that talked about that in this conference. We're now going to be talking about monitoring. We have this model in production. Now, what do we do? And if you do want to actually delve into some of the details of the examples, we have over 50 different examples deploying models from PyTorch, TensorFlow, XGBoost, scikit-learn, and many other things like A/B test, complex routing, multi-arm bandits that you can check in the repo. Again, all of this is in the link that I provided earlier. Before delving into it, let's just have a look. Let's take a step back and have a look at what is the anatomy of production machine learning. And this is basically to get an intuition of what is the ecosystem that we're going to be interacting with. So the anatomy would look as follows. There is going to be a step, which we will call experimentation, that converts training data into these trained models, which we can call artifacts. Now, this can involve many different components like hyperparameter tuning, training, evaluation, etc. Once you have these models, the objective is to actually productionize them through some sort of either manual or automated process, which could be continuous integration, to then have your deployed model. And all of the inputs and outputs that goes into your model, those would then be ideally audited so that they're reproducible. But this still lies the question of where are the metrics? What is the monitoring that we're going to be using? The 4 core pillars that we're going to be diving into today include the traditional microservice metrics and tracing, the usual monitoring that you get with a non-machine learning service that you may deploy an application, you would expect the same for a deployed model, right? Yes, it's a machine learning model. Yes, it's more advanced, but it's still a digital asset that you need to manage like your other services that are running. We're going to then have a look at some more specific machine learning statistical performance, and then some more advanced machine learning monitoring that the different frameworks that we're going to be covering, Seldon Core, Alibi, enable us to do, including drift detection and outliers, as well as explainability. Again, we're going to only do a whistle-stop tour, only cover it from a very high level, but if you do want to see it at your own pace, you'll be able to actually go through all of the examples in the blog post, as well as the Jupyter notebook included. So let's dive straight into performance monitoring principles. So this is specifically in the context of the same things that you would have and that you would monitor for non-machine learning models, non-machine learning services. So this is the performance of your running service to identify potential bottlenecks or runtime red flags, and to debug and diagnose any perhaps divergent performance in regards to the services, like the latency or the request per second. Now, the key concept that we're dealing with this here is not single models being deployed, but the context of we're dealing with hundreds, if not thousands of models. So we can't just expect everything to be wrapped in a custom Flask wrapper and all of the metrics to be custom through different ports and different endpoints without any sort of consistency, as otherwise it would be impossible for the DevOps or platform teams to be able to manage this at real scale. And the key thing that we're going to be presenting here is not just how to do it for a specific model, but what are the architectural patterns that we can adopt that will really allow us to achieve this at massive scale. And the first pattern that we're going to look at here is for the performance monitoring patterns. Once you actually convert your artifact or your code for the machine learning model into a fully fledged microservice, with Seldon Core, you get out of the box metrics that are exposed for Prometheus to consume, as well as functionality for tracing to know what is the potential latency across every hop of your microservices. So from that perspective, you have, for every model that you deploy, key things, regardless of whether your model is TensorFlow, scikit-learn, XGBoost, PyTorch, etc. You get some core metrics that tell you the health of your existing running component. And from that perspective, you would be able to get some simple things. In this case, with our deployed ResNet32 CFAR model, we can see our latency with the different percentiles to see if perhaps one out of every X number of requests may take a significant amount of time, which may tell us that we perhaps may need to increase the number of CPUs for our pods or for our running microservice, the number of running horizontally scaled microservices, or whether we need to perhaps take into consideration other optimizations that then could go deeper into the machine learning, but initially it could be seen more as just a general health services of the microservices. And from that perspective, now we start asking the question, well, okay, that's well and good. Anyone could do that. Well, not anyone, but that is already known. How do we now start delving into more machine learning specific metrics, such as the accuracy, precision, recall, RMSE, KL divergence of my running model? And remember, this is not your offline experimentation, label data. This is unseen data, unlabeled data that is going real time through your models. So how do you introduce what we can refer to as stateful metrics when it comes to models that are currently running and are deployed and are processing data in real time? And this requires the introduction of not just the ability to request predictions, but also to be able to provide feedback or annotations, relabeling, reannotation of the correct label for predictions that may have gone through the model before. And we'll see what this means, maybe if this is a bit confusing. And this will allow you also to be able to perform benchmarking of an older model and a new model, right? You may want to see how they perform in regards to data that may not have been available in your training, but may now be available, that it has been reannotated in production through some manual process, right? In some cases, you may have some automated, but many times it may have to be manual through domain experts. And before we delve into the details, we also need to see what is the architectural pattern that is going to allow us to scale this. And the way that we have been able to expose it through Seldon Core is by introducing what I mentioned, the ability to provide feedback. So whilst when you send a request, you get the response for the inference, you can also make sure that the request gets actually stored in a key value store, in this case, Elasticsearch, with its unique request ID. Once you actually have the unique request ID, some domain expert can actually then provide the correct label asynchronously at a later date, which then instead of actually being calculated within the model, this would get forwarded into the respective, what we refer to here as metric servers. These are separate components, separate microservices that all they do is able to take that new incoming feedback and then check against the initial inference request and compare it to see if it was correct or incorrect, and then expose the raw aggregates such as the true positives, true negatives, false negatives, the probability of each of the predictions, such that then you can actually build those higher level metrics like the accuracy of your model, the precision, the recall of your model. And also the reason why we have aggregates is to be able to ask the questions of what is not only my global accuracy, but what is my accuracy for this chunk or for this period. So this is basically going back again, how can we adopt architectural patterns that is going to allow us to scale this to not just dozens, but hundreds, if not thousands of models. And from that perspective, this can be extended not just to the types of metrics that we mentioned, but also, recurrent-based models such as, RMSE, or even for other specialized metrics like, KL divergence. And then being able to have a breakdown, not just the accuracy, precision, and recall for your model, but also on a per class basis if it is a classification exercise. So this is where you start actually seeing the value of being able to abstract these machine learning concepts into infrastructural patterns that then, allow you to scale with the number of new models that you put in production. So that's basically on statistical patterns, statistical monitoring. Again, if you want to try it out, it's covered in much more detailed in the blog post. This is just more, I guess, to whet your appetite and see the potential of this different architectural patterns. And now just to give you an idea of what the code looks like in the metric server. So all this does is the ability for you to have a separate component. The reason why it's separate is so you don't have to modify the code of your core model component, and you can still get the benefits of this. And you are able to then expose the relevant metrics, which in this case are the true positives, false positives. And this is where you can actually add your own metrics as you find relevant. Now let's dive into the next space. We had to merge both outlier and drift because we don't have much time. But again, in the blog post, they're covered separately because they're not the same. And ultimately, the patterns, you will see there are some similarities, and this is why we can group them, but there is still some nuances that make quite an interesting breakdown once we cover them. So for the outlier and drift detection principles is to be able to make sure that you identify either data that perhaps doesn't fall on the distribution on a per instance basis, or to be able to detect drift into the data that you're seeing or that the predictions of the model that you're seeing. So from that perspective, this is important as this will allow you to trigger the relevant operational processes, whether it is for somebody to just have a look at that specific data point and be able to then leverage other of the different machine learning advanced monitoring components that we've touched upon, or to be able to then trigger other actions, such as perhaps if drift is detected, there may be a requirement to retrain the model, right? So those are the key things that now need to also fit within the architectural patterns that we are seeing now. From that perspective, we're going to be using one of our open source libraries called Alibi Detect, which has a broad range of different drift detection and outlier detection techniques, all of them which you can try yourself, all of them which you can deploy next to your models. And using these architectural patterns, they can actually provide with very abstracted interfaces that can actually plug and play across different situations. For the outlier detection algorithm, we're going to be showing how to use variational autoencoder. In this case, we're going to be able to detect a very obvious outlier with a modified mark in our image of the truck. And this is just basically what you're able to see in how the techniques how the techniques approach the outlier detection internals. But of course, in this case, we're not going to be able to delve into details. What we're going to be doing is deploying it, right? Similar to a model, you are also deploying an advanced component. So you need to make sure that there is the same level of governance with this other machine learning component. And similarly, you have to have the right architectural patterns that allows to scale this. Here you will see some similar things to what we referred to before. For every input request that gets sent, it still gets forwarded to this serverless eventing architecture, which then other microservices can listen to. In the previous case, we had a metric server. In this case, we have an outlier detector server. So this would be a prepackaged server that loads that outlier detector and that is able to process any instance that goes through it. Where the result would then be able to be stored in the Elasticsearch database with that request that came in, and you would be able to then trigger any follow-up actions once you detect an outlier has been sensed. Now, from that perspective, the reason why it's separate is also because of the two main reasons. The first one is to allow you to have this without having to modify your model itself or the actual logic of your model. And the second one is so that it can actually scale, right? If you want to have 2 outlier detectors, 3 outlier detectors, and 2 metric servers, that is ultimately still scalable, leveraging those different data flows that we have introduced. And for the drift detection, we're going to follow a similar set of steps, but with, of course, different concepts and different algorithms. We're going to be showing with another of the techniques that are available within Alibi Detect. In this case is the Kolomov-Smirnov technique, which will allow us to actually detect drift. Now, the key thing for this is that unlike outlier detectors, drift doesn't act on a single data point. It acts on a window. And what that means is that in our architectural pattern, we are not going to be able to action as every single one component, as every single one data point gets processed. We're actually going to be acting on a sliding or tumbling window, right? That means that whenever we reach the window size, then a drift inference cycle can actually be processed, and then the drift result can be exposed. This is also the reason why, in this case, we don't have the one-to-one mapping with the input request into the Elasticsearch database, because it's not a single request to a single drift. It's basically the group into the particular result. However, as we discussed, these metrics that are provided, we are able to then trigger actionable insights that don't only tell us, okay, well, there's drift, but then there's the question of, well, what should happen when that is identified? Whether it is an automated retraining pipeline or whether it is a slightly more manual process where a domain expert or data scientist will then have a look at that data set and that sample that was used and make a decision, educated decision based on that. And there is a question of, it would be one outlier detector server for each deployed model. That is a really good question. So one of the things that we have been exploring with Seldon through several working groups is the concept of multi-model servers. So through one of our projects called ML Server, which is also open source and you can find it in the repo, we have provided functionality for multi-model serving. Conscious of time, we're not going to be able to delve into this, and I'm actually going to have to rush through some of the different components. But yeah, similarly, you can see that now with the monitoring, you can actually see some of the outliers that are exposed. In the blog post, you can try it yourself, and similar for the drift. Now, for the explainability components, this is probably something that you have seen in the past before. However, you most likely may have come across through this in the context of offline data when you're training your model in your Jupyter notebook. From this perspective, we're now going to be able to see the architectural pattern that is going to allow us to scale this in production. So if we are to deploy an explainer, that we may actually leverage our Alibi Explain library, which, similar to the Alibi Detect, we have a broad range of different techniques, including SHAP, counterfactuals, anchors, etc. But the pattern would just be the only difference that instead of sending a request and getting a response of the inference, you would send a request to the explainer, and it would actually reverse engineer the model still as a different microservice for black box explanations and return the actual explanation result. Of course, for white box explainers, we actually load the model there. And of course, we're not delving into all the details of how we also abstract the concept of downloading artifacts from buckets or different locations. but you can try that yourself, and you'll be able to see how all that works. So, there's a lot of things to consider when it comes to explainability, but there is always the requirement to make sure that you have the intersection of the data scientist and the platform expertise. And I guess just to go into the code, from that perspective, you have the similar explanation techniques that you may have seen. You're able to see how the model, predicts what it predicted. So from that perspective, you can also check out other techniques like adversarial detectors, which are covered in the Alibi Detect framework, as well as adopting some of these architectural patterns in more advanced techniques. So you can actually have a drift detector with that architectural pattern running on top of a metric server of a model. So you can see how these abstractions allow you to have a greater power when it comes to these different things. And just to kind of wrap up on a note, one of the things that we didn't cover, but is still equally important when it comes to machine learning monitoring, which you will be able to again find in all of the resources that I provided in the link, is things around alerting, around introducing service level objectives and indicators, progressive rollouts, and then being able to leverage all the data that you're storing for drill downs on metrics. So please do feel free to check it out. Today we covered a lot of content, but fortunately, all the content, you can find it offline. And if you have any questions, you can join the Seldon Slack, where you can post any questions. We've actually had a lot of people providing feedback and thoughts on that specific topic. So with that, I'll leave it there. Thank you, everybody, for holding through this very active and packed session. If you have any questions, please feel free to put them in the chat, and I'll be able to answer them. And please visit the link if you want to check out all of the different things. Thank you very much, and I hope you enjoy the rest of the conference.
Yeah, thank you so much, Alejandro. Really appreciate it. Yeah,
awesome. And I'll probably until either they kick me out, or if there are any questions on the chat, please feel free to post them, and I'll try to answer as they go. And if not, I hope you also enjoy the conference as well.
For the polls and give us feedback, please. That will be definitely very helpful for us. Alejandro,
a lot of thanks. Thank you everybody for joining. I think Kushal, Ivan, Priyansi, thank you. Thank you for joining. Really appreciate it. And also, thanks to Bruno for that question. If you're curious on the multimodal serving, that's something we also are currently exploring. And we are going to be very keen on also exploring it in the context of advanced machine learning components. There's a question. So what is the ethical AI integrated here? I guess just some nuance into the question. There is no such thing as an ethical AI, but there is a set of tools that then will allow domain experts to introduce processes to make sure any ethical implications are taken into consideration, and potential undesired outcomes can be mitigated. There is a broad range of different tools that were only skimmed through in this session, but the explainability tools are probably the most relevant one. If you're interested, to check out the Alibi Explain project. So if you just search on GitHub or Google GitHub Alibi, you'll be able to find that project. We have a broad range of different explainability tools that by themselves allow you to, as they say, open the black box and explain the model's predictions. And basically, as you say, fairness, bias removal, you are able to then leverage some of those techniques to be able to introduce into your processes. But of course, there is going to be existing human operational processes that would have its own ethical nuances, and those will have to be taken into consideration by the cross-functional teams of domain experts that would be able to combine these advanced machine learning techniques with the relevant domain expertise and the relevant touch points, right? So when should who check to make sure that there is a right sign-off? So those are the key things to consider. So there's another question. What are the future plans, directions for Seldon? So we actually have, we have our community call starting right now. If you want to find out for the current plans, you can join that. But yeah, we actually are currently planning to delve further into monitoring. We already have some functionality. However, we are looking to introduce more advanced components like progressive rollouts, as well as other techniques. And yeah, I think there's another question.
Yes.
And then there is, do you need to train the drift outlier detector for a model, or it can be automatically detected for you? That's a great question. So unfortunately, well, fortunately and unfortunately, you do have to train outlier detectors. And this is interesting because now you see that the outlier detectors are also models. So when you're deploying a model and you may think to yourself, oh, I'm going to deploy an outlier detector to reduce the risk, you are reducing the risk of that model, but you're introducing a new model. So there is another monitoring heuristics that you need to take into consideration for that new digital asset that you've deployed. So that is why we are adopting this as architectural patterns, as opposed to just, hey, look, this is a shiny tool you can just use, right? More around, this is the tool, and these are the patterns that you can use to scale it. So those are the I guess, the perspectives on that. But yeah, I mean, I think I've already delved into quite a lot. So it's probably a good note to wrap it on. So with that, once again, yeah, thank you for everybody. Thank you to everybody. Thank you for joining, and I hope you enjoy the rest of the conference. So yeah, bye for now.
Thank you.